Hello all, welcome to Operations Research course. We are formulating integer programming problem examples, and in this lecture we are going to formulate a very well-known problem, which is the assembly line balancing problem. We will consider two different versions of this problem. We will formulate two different of the problem in this lecture. So let's get started. So in this lecture, we will learn how to formulate assembly line balancing problem. In fact, there are different versions of this problem. Today, in this lecture, we will learn two different versions, how to formulate two different versions of the problem. Let's start with the first version. The first thing is to understand what the problem is. It says that there are 5 workstations. So let me represent these workstations here. This is one workstation, this is another, third one, fourth one, and fifth one. So these are workstations. Okay, the workstations basically may consist of machines or workers that perform a number of tasks on the material. And simply the raw material enters here and some assembly operations are performed in the first workstation, then it moves to the second one, some other operations performed in the second one, and it moves to the third, fourth, fifth, and then the produced or assembled part leaves the line. Okay, so this is how an assembly line works, and in this example we are said that there are 5 workstations. And it says that the jobs to be processed in this assembly line requires 8 operations. And this diagram over here shows the precedence relationships between these 8 operations. So this is operation 1, operation 2, 3, and up to this 8. And an arrow like this shows the precedence relationship. What does a precedence relationship means? It means that this assembly operation 1 must be performed before assembly operation 2. Okay, similarly, assembly operation 2 must be performed before 5 and 4. Okay, also for assembly operation 6, in order to start this assembly operation 6, this assembly operation 4 and 5 must be completed. Now the problem is this. We have these restrictions of orders between the assembly operations, and we have 5 workstations and 8 operations like this. The problem is to decide at which workstation these operations, assembly operations, will be performed. Okay, so let me give an example. Let's assume that assembly operation 1 is performed here, and let's say 2 is also performed here. Okay, so this 4 over here is the time of the assembly operation 1, and 10 is the time of the assembly operation 2. So if we allocate both of these operations to the same workstation, then the total time of the workstation will be 4 plus 10, 14. Okay, and then, for example, the third operation can be assigned here, and the fourth operation can be assigned here, and the fifth one also can be assigned here. In this case, what do we have? The total time will be 2 plus 6 plus 13. So the time of the first workstation in total is 14, and the time of the second workstation is 21. Similarly, you continue to assign the operations to all these workstations. At the end, let's assume that 14 is the first workstation's time, 21 is the second workstation's time, and let's say this is 12 is the third one, and 15 is the fourth one, and 20 is the last one. These are the total time of the workstations. Then the production time of this assembly line, or the throughput rate, depends on the slowest station. The station with the largest processing time determines the production rate. Therefore, we try to reduce this total time as much as possible to increase our production time. Okay, the slowest one, called the bottleneck station, determines this time, and this time of the slowest station, which is 21 is in this example, is called the cycle time of the line. Okay, it means that in every 21 minutes, one part will be produced. Okay, it doesn't depend on this one, 14. It doesn't depend on this one, 12, because in order to process a part, you need at least 21 minutes. So in every 21 minutes, you are producing one part, and we want to reduce this time as much as possible by determining the allocation of these assembly operations to workstations. Of course, allocation of the operations will change the time of the workstations. For example, here, instead of allocating this to this second task to this second workstation, if I this third task to second workstation, if I allocate it to the second one, what would happen? This 14 will be plus 2, it would be 16, and this 21 would be 19. And as you can see, now the slowest station is this one, and the total cycle time reduced from 21 to 20, which means that this allocation is a better one. Okay, so the problem is to decide on these allocations, but we have these precedence relationships, and let me give you an example how precedence relationships should be considered. So assume that in this example, we allocate this task 4 to the first workstation. So in the first workstation, I have task 1, 2, and 4, and in the second one, I have 3 and 5. Okay? If you look at the time of this, it will be 4 plus 10 plus 6, and the second one will be 2 plus 13. But there is a problem here. Look at this task 3 and task 4. Okay, look at this relation over here. Task 3 precedes task 4. It must be completed earlier than task 4, but look, task 4 is assigned to an earlier workstation, so this is not a feasible solution according to this precedence relationship. So this precedence relationship simply says that a task, if a task precedes another one, it must be assigned to an earlier station, but also it can be assigned to the same station. Okay, it is also okay if they are assigned to the same station. It means that if instead of assigning 4 to the first one, if I assign it to the second station, so in the second station now I have task 3, 4, and 5. This task 3 should be completed earlier than 4 and 5. And in the same station, I can arrange the order so I can process first, third operation, then fourth, then fifth. Okay, so I can do this. So it means that if there is a precedence relationship between two operations, sometimes we call it tasks. Okay, if there's a precedence relationship, then the preceding operation cannot be performed later than the succeeding one. This is the precedence relationship. Okay, now we know all the details about the assembly line balancing problem. We want to assign these operations, assembly operations, to these workstations, so that we want to minimize the total time of the slowest station, and we want to satisfy these precedence relationships. This is the assembly line balancing problem. Now take a minute, stop the video here, pause the video here, and take a minute to think about how you can formulate this problem. What is your decision? What we are trying to decide on, and how can we define the decision variable? And then using that decision variable, how can I write my objective function, which is the minimization of the cycle time, which is the minimization of the time of the slowest station? And then how can I write the necessary constraints? Okay, take a minute, please, and then continue to the video. Okay, now I hope that you had some idea And let's formulate it all together. Here our decision is to decide on the assignment or allocation of these operations to the workstation. So my decision variable should be related to this assignment. And remember this assignment problem that we already formulated. We will use a similar decision variable here. In assignment problem, our decision variable had two indices. For example, we wanted to assign a task, a worker, to a job. This would be something similar, but of course not exactly the similar, because in assignment problem, we were assigning each job to only one worker. But here, we can assign more than one tasks to the same workstation, okay? So I'm not saying that this formulation is exactly equal to the assignment problem. I'm just saying that the decision variable that we are using is similar to that one, okay? Don't be confused. So this xji will be a binary decision variable, and it will take the value of 1 if task or operation j is assigned to workstation I. Okay, so I'm representing the operations by j, and in this example I have 8 operations, and I index, I'm using it to represent the workstations, and I have simply 5 workstations, and it will take the value of 0 otherwise. Okay, now using this decision variable, I should be able to write my objective function. An objective function is the cycle time, which is the largest processing time of the workstations. As I told you, if we assign operations 1 and 2 to the first workstation, the total time will be 4 plus 10, the summation of the processing times of the assigned operations. Okay, so how can I find this time? So look, remember, x11, what does this represent? This one represents the operation 1, and this one represents the workstation 1. And if this is equal to 1, it means that operation 1 is assigned to workstation 1. What about x21? Operation 2 assigned to 1. What about x31? Operation 3 assigned to 1. Okay, similarly, if you go in this way up to x81, it represents if operation 8 is assigned to workstation 1 or not, depending on the value it takes. And I know the processing time of operation 1, which is 4. So if I multiply this processing time by x11, if this is equal to 1, then it means that the processing time on the workstation will be increased by 4. Otherwise, if it is 0, there will be nothing. Okay, the second workstation time is 10. 10 times x21 will give me the, if the second operation is assigned to workstation 1, it will give me, or it will increase the processing time of this station by 10 units. And if I do this calculation up to the 819 times x81, so this summation here will give me the processing time of the first workstation. So let me represent it as P1, the processing time of the first workstation. The processing time of the second workstation will be, okay, again, it depends on if this first task is assigned to second station, or if this second task is assigned to second station, up to this last one is assigned to second station. And we have in total 5 stations, 4 times x15, 10 times x25, up to 9 times x85. Okay, so depending on a solution, for example, if x11 is equal to 1, x21 is equal to 1, x32 is equal to 1, and etc. Depending on such a solution, when you plug in the values into these calculations, they will give you the processing times of the stations. Okay, so these equations give me the times of the stations, but the thing is, the objective function is the slowest one. How can I find the slowest one? Okay, if this is 12 and this is 21 and this is 15 and the other one is 14, the other one is 20, the slowest one is this one, right? 21. So what is that slowest one? Actually, it is the maximum of these P1, P2, up to P5. If I find the maximum of them, then it is the slowest station. So what I am trying to do, I am actually trying to minimize this maximum of P1, P2, up to P5. Okay, I'm trying to minimize this maximum. And P1, P2, P3 are actually these. So how can I represent this in compact form for P1? So I'm going to say that this time of operation for the first task, I'm going to represent it by T1. This will be T2 and this one will be T8. Okay, so I will multiply this by Tj, this is the task time of the j task, multiplied by xj1. And if I sum this j from 1 up to 8, it is this first summation. What about the second one? In the second one, simply I will replace this 1 by 2. Okay, so if I write it as xji, then this summation will give me pi value. And in order to write this in compact form, I can simply do this. I can write here maximize j from 1 to 8 tj times xji, and how many processing times are there? There are 5. Okay, so my objective function will be this in compact form, and in open form you can write this maximum of this one and this one and this one. Okay, this is my objective function. Of course, I will have a number of constraints, but before moving to those constraints, there is one observation that I need to make. And what is that observation? This objective function is not linear. It's a min-max objective function. And remember, how do we linearize a min-max objective function? Simply, we say this maximum to be a variable, which is z, and we write our objective function minimize z. And then we write the constraint subject to, if this z is the maximum of these, it means that z should be greater than or equal to each one of them. So actually my constraints are like this. Z should be greater than or equal to first processing time, second processing time, the last processing time. Okay, so I can write this in compact form. This z should be greater than or equal to j from 1 to 8 tj times xji, and I'm going to write this for all I values. Okay, I from 1 to 5 for all stations. So it simply says that this, I am trying to minimize this z, which z represents the maximum processing time, and this maximum processing time should be greater than or equal to the processing time of all workstations. There are 5 workstations, and this largest processing time should be greater than or equal to each one of them. And instead here, look, we used z, but what does z represent? Z represents the cycle time. So instead of using z as a decision variable, I can use another representation, which is tc. This represents the cycle time, okay? So it is more easily readable. That's why we change it. tc means the cycle time, that's it. Okay, so this is my objective function. So let me write it here, the final model. We are minimizing the cycle time such that this cycle time should be greater than or equal to each one of these processing times, Tj times Xji, for all I from 1 up to 5. Okay, so this is the objective function, the linearized version of the objective function. Okay, what constraints do we have other than this linearization constraint? You would say that we have precedence constraints. Yes, of course, we have precedence constraints, but before that precedence constraints, there is one more constraint which is not stated here. What is that? If I just write this model into Cplex and try to solve it, all xji will be 0. Why? We are trying to minimize the total time. If I don't assign any one of these operations to any one of the stations, then their time will be 0, and that's the minimum possible cycle time, right? 0. So there is one implicit constraint here, which actually we need to satisfy that all tasks, all operations must be assigned to one of the workstations. Okay, so this task 1 must be assigned, task 2 must be assigned, and they must be assigned to one of the workstations. So let's write that constraint. So for the first task, this first task can be assigned to the first one, or it can be assigned to the second one, or to the third one, to the fourth one, to the fifth one. So it can be assigned to only one of these, and it must be assigned to only one of these. And this is the constraint for task 1. And similarly, this is the constraint for task 2. Second task must be assigned to any one of these 5 workstations. Okay. Now, of course, we are not going to write it in such open form, but we will represent it. We will write it in closed form. And in closed form, we say that the xji summation over j from, I from 1 to 5, xji should be equal to 1 for each task. And how many tasks do we have? There are 8 tasks in this example. Okay, so this is the assignment constraints. The first one is linearization constraint. It determines the cycle time. The second one determines the assignment. Now we have the third one. And the third one is an important constraint, which is the precedence relationship. We need to write these precedence relationships as a constraint. And how do we write it? Again, think about the idea of precedence relationship. It says that if, let's say, task 1 precedes task 2, then the task 2 cannot be assigned to an earlier workstation than task 1. This is not possible. The station that this task 1 is assigned to must be earlier than task 1. But of course, for this, we need to know if there is a precedence relationship between 1 and 2. And it is given in this graph, but actually we cannot use that graph in Cplex. We cannot just enter a graph into Cplex. We need to give data, numeric values, tables, matrices. So we cannot give a graph into Cplex and say that understand the precedence relationships by this graph. So what we are going to do is we will convert this graph into a matrix, a data that we can use in Cplex. Of course, there are different methods, but I'm going to use this method to you. And what we are going to do is we will have such a table. representing each row will represent the tasks. So there will be 8 tasks. And similarly, each column also will represent the tasks. So it will be an 8 by 8 table. Okay. So what does it show? So if this number over here is 1 for row 1 and column 2, it would say that task 1 precedes task 2. Okay, if nothing is written, it means it is 0. Okay, then it means that there is no precedence relationship between these two tasks. So between 1 and 1, so there is no precedence relationship. Between 1 and 3, look at this graph, 1 precedes 3. Between 1 and 4, there is no direct precedence relationship, so you don't need to write that one, so it is 0. 1 and 5, 1 and 6, 8, and 7 and 8, they are all 0. So 2 and 1, there is no precedence relationship. 2 and 2, 2 and 3, 2 and 4, 2 and 5, and others. 3 and 0, look, 1 precedes 0. 3 does not precede 1, so that's why this is 0. 3 and 2, as you can see, there is no precedence relationship between them. 3 and 3, it cannot precede itself. 3 and 4, and all others are 0. So we are going to convert this diagram, precedence diagram, into this matrix. And then we will make use of this matrix, and we will represent, in order to be able to write this in a compact form, we will represent these values as a parameter, and the parameter will be bjk. Okay, so this bjk, what does it mean? For example, this value over here is b11. This value is b12. And what is that value? It is equal to 1. It means that task 1 precedes task 2. Okay? So bjk is a parameter which takes only 2 values, and it takes the value of 1 if operation j precedes operation k and 0 otherwise. Okay, so here b12 is equal to 1, b11 is equal to 0, and everything is written in this table. Now, don't be confused when I write this bjk in this way. Some of you may assume that, okay, this is a decision variable. It's like this xji 10 and bjk 10. The thing is, this is a parameter, this is a decision variable. What was the difference between a decision variable and a parameter? It is this. For a parameter, we already know the values before solving the problem. The decision variable, we don't know the values before solving the problem. We only know the values after solving the problem. Okay, so do we know all these values before solving? Yes, it is given here. We just converted it into this table and we know their values. That's it. It's a parameter. Now I'm going to make use of this parameter. But before this parameter will be needed to write the model in compact form. Okay, before writing it in compact form, let me write it in open form so that we understand the idea, and then we can convert it to a compact form. So I'm going to write this open form into this small area over here. Now let's have a look at the relation between 1 and 2. Okay, what should we say? We should say that task 1 should be assigned to an earlier or to the same station with task 2. Okay, so or the station that this task 2 is assigned to must be later than or equal to the station that this task 1 is assigned to. Okay, so for this I need to know which station this task 1 is assigned to and which station this task 2 is assigned to. But of course, before solving it, I don't know. But this decision variable that we defined identifies that information. So let me write it here. In order to find the station that this task 2 is assigned to, I can do this. Okay, so x21 represents if this task 2 assigned to station 1 or not. Okay, this task x22 represents if task 2 is assigned to station 2, 23 if it is assigned to 3, if it is assigned to 4, and if it is assigned to 5. So these are the decision variables related to task 2. Okay, only one of them can be 1 because a task can be assigned to only one station, and this is the result of this constraint. So it means that, for example, this can be in a given solution. This is just an example. If one of them is 1, all others must be 0. And what does it mean? It means that this task now is assigned to station 2. And I need to understand what is the station number. And for that, I do this calculation. 1 times x21, this one is station 1, plus 2 times x22, okay, station 2, plus 3 times x23, plus 4 times x24, plus 5 times x25. Okay, so if I do this multiplication, if I do this summation, what happens? If this is equal to 1, then the value is 2. And what is 2? It is the station number that this task 2 is assigned to. If you say, no, this is not 1, this is 1. So it means that this is 0 and this is 1. And the station number will be given with this equation to be 3. So I understand to exactly which station this task 2 is assigned to by this formula, by this calculation. So I can do the same thing to understand the station that this task 1 is assigned to. So x11, so 1 times x11 plus 2 times x12, 3 times x13, 4 times x14, and 5 times x15. So this summation gives me the station that this task 1 is assigned to. Okay, so this is for task 2, and this is for task 1. And what is the relation? Task 1 should be, task 1 precedes task 2. So it means that the station number of task 2 must be greater than or equal to the station number of task 1. That's it. So this is the precedence constraint. And I have written this constraint between 1 and 2. But I need to write this constraint also between 1 and 3, between 2 and 5, 2 and 4, 3 and 4. So for all these precedence relationships, I need to write this constraint. Okay, so let me write another one, give you another example, an open form, and then we will convert it to a compact form. Okay, so let's have a look at between 5 and 6. Okay, so there's a precedence relationship between, look, I'm not writing a constraint between 2 and 3 because there's no precedence relationship between them. I'm writing this constraint only for the tasks that have a precedence relationship. So what I am doing, if 5 precedes 6, I'm saying that the station that this 6 assigned to, which is found by this 1 times x61 plus 2 times x62, x63, and 4 times x64 plus 5 times x65, this should be greater than or equal to the station that this task 5 is assigned to, which is 1 times x51 plus 2 times x52 up to 5 times x55. Okay, so this is the station that this task 5 is assigned to. Okay, now how can we convert this into compact form? this summation over here, what is it? If I want to write it as a summation, so I would say that it is I from, we are summing over the stations, I from 1 to 5, it is x6i, right? 6, 1, 6, 2, 6, 3, so 6i. And I'm multiplying each one of them with the index I. So it is I times x6i. And we want this to be greater than or equal to what? Again, I from 1 to 5, again summing from over the stations. And this time it is x5i. And again, it is I times x5i. Okay, so this is the compact form of this equation between 6 and 5. But still it is not in compact form because I need to repeat this thing between 1 and 2, 1 and 3, 1 and 4, and etc. So if I convert this into this form and just say that, okay, summation I from 1 to 5, I times xki, sorry. It is actually just an index, but not that important. But let me write in this way. Xki will be greater than or equal to. So I'm considering two tasks for which j precedes k. So I'm writing a constraint between these two general tasks. Okay. So I'm first writing the second one, k. And now I'm writing this again, I from 1 to 5, I times xji, and I'm going to write this for all, okay, for all j and k, for all tasks, and such that j not equal to k, so that there is no precedence relationship between 1 and 1, 2 and 2, okay, j and k different. But of course, what should be the case? This j and k must have a precedence relationship. Like in this one over here, 2 and 3 doesn't have a precedence relationship, so I shouldn't write this constraint. If only there is a precedence relationship, I should write it. And actually, there are two methods to write it. The first method is to, let me not confuse you with two methods. I will just give it here only a single method. And it is to multiply this by bjk. Okay, the second part. So what does it mean? If bjk is 0, for example, b14 is 0, what does it mean? There is no precedence relationship between 1 and 4. And if this is 0, this right-hand side appears to be 0, and it says that this left-hand side is greater than or equal to 0, which is always satisfied. So this constraint becomes a redundant constraint. But if, for example, 1 and 3, between 1 and 3, if it is 1, then we have this constraint saying that this 3, k is 3, and j is 1, okay, I need to write this constraint for 1 and 3. And that's it. This is the formulation. Of course, you need to say that this xji is a binary decision variable for all j and I, and also this tj is the cycle time, is a continuous decision variable. Okay, so this is the assembly line balancing problem formulation for the first version of the problem, in which we know that there are 5 workstations and we want to minimize this total cycle time. Now let's formulate a different version of this problem, and basically it will be very similar to this one, but still there would be some differences. Let's see, first let's see that different version of the problem, and then let's formulate that one. Okay, in the second version of the problem, The definition of the problem is a little bit different. So it says that now the desired cycle time for this line is 20 minutes. Okay, but we don't know the number of workstations to be used. And the objective is to determine this, how many workstations should we use in order to minimize the total number of workstations, because setting up new workstations is costly. We want to minimize the cost of establishing these workstations actually. So when we minimize the number of workstations, that cost is automatically minimized. So actually now in this problem version, there are two decisions. One decision is how many workstations or which workstations we are going to use. And in the second one, similar to the previous one, which task should be allocated to which of the workstations. Okay, these are the two decisions. So this problem formulation again have similarities with the previous one, but also have differences. And on the other hand, in order to formulate this one, yes, we need to decide on how many workstations we are going to use, but we need an upper limit on the number of workstations. I mean, at most these many workstations we can use. And actually we can know that number. Look, how many tasks are there here? So 1, 2, 3, 4, up to 8 tasks, 8 operations. So we cannot divide these operations into smaller elements. These are already the smallest elements. So it means that we can assign these tasks. If we assign each of these tasks to a different workstations, we will use at most 8 workstations. At most 8. But the question is, what is the optimal number? Then in order to formulate this problem, similar to the previous one, we again use yji to indicate if operation j is assigned to station I and 0 otherwise. So look, again I am using the station index I. And here j is the number, the operations, and it goes from 1 to 8. And I is the number of stations. And how many stations do we have? We don't know. And for this purpose, we are going to use this upper limit, upper number. And we will say that it will go from 1 up to a big M. This is the upper limit on number of stations. Okay? And this upper limit may be selected equal to the number of tasks, which is 8. And this is our first decision. And the second decision will be included by yi, again 1 and 0. It will take the value of 1 if station I is used and 0 otherwise. So we will assume that, like this, we will assume that there are 8 possibilities, 8 workstation alternatives. We will try to assign these tasks to these workstations. If we assign a task to each one of these workstations, it means that we are using all of them and the number of workstations will be 8. But if we assign these tasks to a subset of these, for example, only 4 of them, and do not use the remaining 4 at all, do not assign anything there, then the number of workstations will be 4. But of course, when you assign each one of these tasks to a different workstation, what will be the cycle time? The first workstation time will be 4, the second will be 10, the third one, fourth one, fifth, 6th, 7th, and 9th. So if this is the case, when we use 8 workstations, and what is the maximum time? It is 15. And the desired cycle time is 20. It means that we need the cycle time should be less than or equal to 20 at the end. And since it is 15, it is less than or equal to 20. And we are using 8 workstations. But the thing is, if instead of having this allocation, if I allocate 1 and 3 to the same workstation, and the total time will be 6 units. And also I can include 2 to the same workstation, 1, 2, 3 to the first one. So I don't need to use a different workstation for this task and another workstation for this task. And still the total time here is 16 less than 20. And instead of 8, we are using 6 workstations. So this is a better solution. And the question is, what is the minimum number of workstations that we can use without exceeding this 20 minutes cycle time? Okay, this is the question. So therefore, what we try to do, our objective now is to minimize the total station number of stations. And how can I find the total number of stations? It is simply this summation, y1 plus y2 up to ym, y8 in our case, will be the total number of stations, because if this is 1, it means that I'm using this. If this is 1, it means that I'm using this. If this is 0, I'm not using this one. And the summation of the used ones will give us the total number of stations. So my objective function will be to minimize I from 1 to this large number of stations, yi. And what are the constraints subject to? Some constraints will be identical to the previous one. What are they? First of all, each task must be assigned to one of the stations. Okay, so here we would say I from 1 to m, and for all j from 1 to 8, each task must be assigned to one of these stations. Secondly, the task time of a station, the total processing time of a station, should be less than or equal to 20. Remember, in the previous case we said that this cycle time should be equal to greater than or equal to j from 1 to m t j x j I for all I. Now here in this constraint, this tc is not a variable, but it is a given number. So simply we will write this constraint. Okay, so I will write in this version j from 1 to m. Sorry, not 1 to m, 1 to, yeah. It is the number of tasks, so it should be 8. So j from 1 to 8, tj times xji should be less than or equal to given cycle time 20 for all stations 1 up to m. This is large M. And also the precedence restrictions are exactly the same. So I'm not repeating that constraint here. Just exactly the same precedence constraint. Okay, but this is not all. We have something missing because we haven't used this yj anywhere in these constraints. It means that if we don't write it here in anywhere, the objective function value will be 0. None of the workstations will be used. For this reason, we need to have a constraint stating that if a task is assigned to a station, it means that that station is being used, or this yj should be equal to yi should be equal to 0 if no tasks or operations are assigned to this station. So simply we will represent this as this xji to be less than or equal to yi for all I from 1 up to m and j from 1 up to 8 in our case, so that if yi is 0, if I'm not using this station I, then I cannot assign any tasks to here. If it is 1, then I can assign. So if it is 1 but I don't assign anything, then this objective tries to minimize it. Why it would make it 1? Okay, if nothing is assigned here because of this objective, it will automatically set the value of yi equal to 0. Okay, so but if at least one task is assigned to a station, then because of this constraint, yi should be equal to 1 as well. Okay, so this is the formulation, and here we would have xji and yi, both binary decision variables for all j and i. So in this second version, look, we looked from a different perspective. In the first one, the number of stations was given in the first ALB assembly line balancing version. The number of stations was given, and we tried to minimize the cycle time. In the second one, the cycle time is given, and we tried to minimize the number of workstations. Okay, so this is how we can formulate the assembly line balancing problem.